So, hello everyone. I'm sure many of you know how much electricity one ChatGPT request consumes. Uh, uh, not Just last week, I've seen some Boavizta members share those some figures about this. For instance, multiple studies found that it was between 1 watt-hour and 10 watt-hour per query. However, which mainly is equivalent to a 10 watt lamp turned on for 1 hour. So that's kind of a known thing right now. But do you also know how much electricity you consume when you use GitHub Copilot for 1 hour? So before doing the study I did, I did not know and I did not care. But right now, I'm going to present to you why you should care. And this is the result of a research paper I've done during my PhD. That's called Green My LLM. You can also find the paper online. Don't worry, I'll share the link of the slides and of the paper if you want after in the chat. So, I don't know if you've noticed, but AI is kind of everywhere nowadays. Almost everyone talks about AI every other day. There's a new comes out and all. But I'm going to talk about something that's a little bit older than ChatGPT. That's code assistance. Notably, GitHub Copilot. For those who don't know, GitHub Copilot is a code editor extension. It's a plugin. Basically, when you are writing in your editor, it will suggest pieces of code that will help you write faster code, basically. That's the main feature of GitHub Copilot. As of today, it has a lot more features, but this is still the core feature of the extension. And there's a lot of code assistants like GitHub Copilot, but GitHub Copilot was one of the first and the most popular one. And I had been using GitHub Copilot since it came out in 2020. I was even a beta tester of it. However, at the time, I did not realize how much energy and resources I was consuming just by using GitHub Copilot. And probably you don't either. And that's what I would like to change today by asking just a simple question. How much energy am I consuming when I'm using a code assistant like GitHub Copilot? So, to answer this question, I have to show you how most code assistants work. Basically, the user writes code, and then the code assistant, which is installed on the user's computer, sends and receives generation requests from and to an inference server that's in the data center somewhere. The actual inference, the actual generation, is not done locally, it's done usually on the cloud. And so what I actually want to measure is here, somewhere on the cloud. And however, in the case of GitHub Copilot, the servers are basically owned by Microsoft and GitHub. And I cannot just go at Microsoft Azure with my wattmeter in hand and be like, oh, please, will you let me measure your application? So we had to find another way to kind of measure what a code assistant would consume in terms of energy. So what we did is that we built a set of what we call development traces, and then we used these development traces to kind of simulate the usage of GitHub Copilot and then measure the inferences. So for the first phase, what we did is that we had 20 participants, 20 human developers that came and developed for a little game in Java for 1 hour, and they were using the real GitHub Copilot. So GitHub Copilot was sending generation requests to its inference server, and normally GitHub Copilot also sends telemetry data to a telemetry server, and the telemetry data is very powerful. It has a lot of information in it, so much so that by just having the telemetry data, we can basically reproduce the whole, we can see everything that happened in the system. So what we did is that we replaced GitHub telemetry server with our own, which did not change the normal behavior of GitHub Copilot. It's just that we capture the logs. And then this allowed us to capture all the telemetry data, which we call development traces. You'll see why in an instant. Thanks to these development traces, we had our telemetry server. We could send back those telemetry data to a code assistant simulator that would basically simulate how GitHub Copilot would interact with its inference server. So what we managed to do is that we resent all the same HTTP requests that GitHub Copilot did to its inference server. And we did that, and we could, as it was a simulation, what kind of a simulation, we could do it as many times as we wanted, and by changing like, oh, we're going to have only one developer using the code assistant at a time, or 20 developers, or 500 developers, etc. So basically, we did that using our own inference server, and which then we were able to measure. So what we measured is the real GitHub Copilot request using our own inference server and LLM. Then we had a lot of configuration options. We could change the number of concurrent developers using the server at the same time. Change if the cancellation of a request was possible. We could change what large language model was going to be used. We could quantize the model or not. We could change the number of GPUs. So in the end, we ended up with a lot of possible configurations, which was too many to test. So we only ended up testing 300 configuration, and we did about 800 simulations. To put it in perspective, each simulation lasts 1 hour, where we resend chronologically all the requests that GitHub Copilot sent when the participant was coding. Before showing you the results, I have some limitations I have to explain. The most important one is that the measures we made are only an estimation of what GitHub Copilot would consume if it was using the exact same hardware as us and the same LLMs. We did not take into account the PUE of the data center, only the energy consumption of the server. And we only considered when we're talking about greenhouse gases emission, we only considered it from the energy standpoint. And of course, we need more diverse configurations. Last but not least, because it was a simulation, we did not take into account what our LLM produced. We did not take into account the quality of what our own LLM produced. So, a few stats. Basically, the less you use GitHub Copilot, the less energy you consume. That seems kind of obvious, but it should be told. And interestingly, the number of requests that GitHub Copilot made to its server varied greatly between participants, between 2 and 20 requests per minute. The main factor of variation was how fast you typed on your keyboard. And interestingly enough, students accepted more often the suggestions from GitHub Copilot than the professional developers, which was quite funny. Here, on this graph, you'll see a representation of all the generation requests that were made by GitHub Copilot, depending on in which state they ended in the life cycle. Basically, what we see is that half of the generations are cancelled before completion. That often happens because the user is typing and maybe the user takes a little pause in the typing, and GitHub Copilot triggers a generation, and then the user begins typing again, and then GitHub Copilot cancels the request on the inference server. We see that 40% of the results are empty. That is, GitHub Copilot asked for a generation. Generation was null or not made because there was nothing to generate. And 20% of the requests were not accepted were displayed to the users, but not accepted. Usually we from user feedback, we get that it was because the user did not specifically ask for the request. So that means that only 10% of the requests sent by GitHub Copilot actually mattered. So what we learned from that is that the automatic suggestion they lead to a great waste of computing power. Interestingly enough, we measured that when we increase the number of concurrent developers on the server, we get a lower energy consumption per developer, such as when there's like 5 developers on the server, each developer consumes about 100 watts. But when there's like 50 developers on the server, each developer consumes about 25 watts. This can go on until what we call a saturation point, until which the server cannot handle the additional load, and the latency of the request basically explodes. I'm going to gloss the technical details in here. Basically, we saw that quantization method generally increased power consumption. We saw that adding GPUs increased power consumption. And we saw that using larger models increased power consumption. Interestingly enough, we found that there were differences in power consumption for models with the same size because they had different architectures. If you want more information about this, you can find the slides online after, or you can ask questions. We had 300 configurations that we measured, and in these configurations, we wanted to show you a few configurations that were meaningful. So basically, we took 3 configurations, one where maybe we simulated 5 concurrent developers, one where we simulated 20 concurrent developers, and one where the server load was maximized. For instance, this is exactly what GitHub Copilot would do with its server, because this is the most cost-effective scenario. And then we also divided these configurations into a frugal and performance objectives, where the energy consumption is minimized, or where the latency of the request is minimized. This is the big table that we found. Basically, you don't have to interest yourself in most of it. The only thing that's really interesting here is the last column. This is basically the column representing what GitHub Copilot would consume if it was using our hardware. What we found out was that developers using this setup would have consumed 20 watts in average power. That is 20 watt-hours per hour. This means that in a normal coding context, each developer would consume about 3 light bulbs worth of electricity. LED light bulbs, obviously. So you can tell me 3 light bulbs, that's not a lot. No, it's not that much. It's about as much as your own computer. But if we take the amount of developers that use GitHub Copilot in the world, or similar code assistants, so we have about 28 million developers. We have 40% of them that use code assistants, especially GitHub Copilot, according to Stack Overflow survey. That leaves us with 11 million users of GitHub Copilot that use it daily. So if we multiply the power consumed by one GitHub Copilot user, and we multiply it by all the users, basically what we get is 235 megawatts. This is the energy that would be needed to power GitHub Copilot if everyone was using it at the same time. Basically, wait, there's a question. If I read well, the average consumption of one query. I answered that a little bit later at the end of the presentation. So basically, this power is equivalent to 1/4 of a nuclear power plant in France. That's a lot just to power this little useful tool. And so that's not all, because according to Stack Overflow survey that happens each year, the numbers are increasing. And the number of features of GitHub Copilot are also increasing. For instance, now there's an integrated chat that uses bigger models such as GPT-4. So what can we do about it? As code assistance providers, if any of you is a provider of code assistance, I would be glad to talk to you. You can use smaller models and more specialized models, like language specialized models, which can afford to be smaller. You can make everything that makes the model consume less energy, and you can, of course, maximize the usage of the servers. And one of the most important thing to our mind is that you should absolutely allow the users to manually trigger the code assistant suggestions, which is not possible in the VS Code as of today. It's possible in JetBrains, but not in VS Code GitHub Copilot, because this is, as we saw, 90% of the requests sent by GitHub Copilot were not useful at all because of that, mainly because of that. As users, you can do your best to use assistants more mindfully and don't make them the default. That this is also applicable to most AI tools as of today. You should think before prompting and only use AI when you need it and not before everything else, because AI consumes a lot of power, basically. And I'm just talking about the energy consumption, but if we go into the environmental impact of the GPUs and the hardware, etc., it's not better. And as researchers or practitioners, we can do our best to measure the environmental impact of AI in general and make the measuring process easier. And most importantly, I think the most important is to talk about it around you, because not much is known about code consumption, and most people don't realize how much it costs. Yeah, Julien wrote something in the chat with it, which is interesting. It's, if you work for a large organization, talk to your customer manager at GitHub and pester them to provide energy estimates as well as costs for GitHub Actions, but also for GitHub Copilot. Yeah, that's totally something you should do so that you can have insights about what your usage is. And by having insights, you can then have levers where to improve your environmental impact. So thank you for listening. I hope the presentation was interesting for you, to you. And if you have any questions, I'm glad to hear them. So to answer Eric Forboul, about the energy consumption of one request. In the case of GitHub Copilot, what we found is that 1,000 generation requests was equivalent to 0.4 watt hour. So yeah, basically one query, because not all queries are the same, would be 0.0004 watt hour. So is there any other questions?
Yeah, just to follow up on that. So it looks like it's very efficient compared to other, estimation of the consumption of any inference. So the next question is, I think I have seen that it was a 7 billion parameters model that you used?
I've used 7 billion and 15 billion parameters models, which are approximately which are the same size as what GitHub Copilot uses or has been using in the past.
Okay. Okay.
I think today it's GPT-4o that is used in GitHub Copilot, if I'm not mistaken. So it's more like a 200 billion parameters model, something like that. So it's...
what you're talking about is a chat model, which has notably a very lower latency and higher cost, and GitHub and Microsoft cannot afford to use it for the inline automatic suggestions that we see. What we know is that when GitHub Copilot launched, it was using Codex, which was a 15 billion parameters model, I think, or maybe lower. And the reason why they use such a small model is because basically for cost and latency reasons, because otherwise it would cost them way too many. And if you look at the latency of the request today, the latency corresponds basically to the latency that one would have with a smaller model and not a 200 billion parameters model. Of course, the latency could be improved for very large models by using more GPUs, but I don't think it would be cost effective for them. So yeah, an important point is also that the GitHub Copilot runs on US-based servers. And yeah, so I took the carbon intensity of French servers, but I think if we take the US servers one, it's way worse. Yes, Eric?
Yeah, it's very interesting. So I come up with a new question. Did you study, did you make a difference between the use of different models? Meaning, do you have noticed a proportion of consumption with the number of parameters of the model?
Is your question, does the size of the model affect the energy consumption?
Well, it does affect, but I guess it looks like it's obvious, but I've seen some publication with a very proportional way to evaluate, in fact, inference consumption with the size of the model.
Yeah, so in our case, if you look at the first line here, basically what we see is the ratio of the energy consumption when switching from one model to another. So when we switch from Starcoder 2 15 billion parameters to Starcoder 2 7 billion parameters, the energy consumption is maybe divided by less than 1.5, excuse me. I mean, the ratio sits between 0.75% and 1. So in some cases, some rare cases, using a smaller model was almost equivalent energy-wise as using the bigger model. But in most of the cases, using the smaller model resulted in maybe like a 30% energy decrease.
Okay.
Does that answer your question?
Yeah. I'm just wondering why there is a ratio of, let's say, 1,000 between what we can see in other studies in terms of consumption per inference.
Yeah, of course. I've thought about it a lot, and this is because of one simple mechanism, which is batching. If I were to send one request at a time in a sequential kind of way to my server, I would end up with energy consumption much like the that we have here. Because most of the time the server is idling and it's not using its full capacity because GPUs have great parallelization power, and what we saw that we can fit up to a lot. We can send a lot of parallel requests, not lose that much latency, and in fact gain overall energy consumption. This is what we saw in this table here. where you see that if I have only one developer using the server concurrently, the energy consumption per developer is really high because additionally to the idle power usage of the server resources are not used very efficiently. But thanks to batching, basically, if we send multiple requests at the same time in parallel, or more or less at the same time, they will better use the resources of the GPUs. And what this means is that by adding a second developer, the latency does not go up twice. It goes up like maybe 1 or 2%, and the power consumption lowers. And the mean power consumption in green. This is the power consumption of the whole server. You can see that it goes up to about 1,000 watts, which is basically the TDP of all components of the GPUs and the CPU. So at some point, the consumption, at which point, there's nothing, adding more users won't yield any additional benefits. So I think that most studies, what they do is that they send requests to a server that is powerful enough use the LLMs, but they do not send enough requests to efficiently use the server, which leads to a higher energy consumption. Is that clearer for you?
Yeah. I'm just. I will check the study to see if they manage, the server load. But I have hard time to believe that they do not. But maybe.
Yeah. The real issue is that the idle consumption of GPUs is really high. In my case, the idle consumption of the server was like 300 watts, and I had just four GPUs. So yeah, that's really a lot. And if you don't take that into account, you're going to bias the.
Okay, thank you.
So before Bruno, Mohamed asked a question. Thanks for the great insight. If we assume that the trigger is manual, shouldn't we compare using Copilot to not using it, the time of coding and the consumptions? Yeah. Originally, the study aimed to observe the time gain using GitHub Copilot or not. The issue is that it's basically impossible to measure the time gained by using a code assistant. It's basically impossible to measure it in a rigorous way and reproducible way and in a way that's generalizable. So we couldn't do that. However, in a future study, it would be very nice to compare the usage of GitHub Copilot with automatic suggestion and manual suggestions. So Bruno Thomas, you were asking a question? All right. So maybe you're not asking a question anymore.
Sorry. Can you hear me?
Yeah. Yeah, I can hear you.
Thanks for your presentation. It was awesome. And I was wondering if there is how it is made about the language, the coding language. Are there some specifics, or are they all mixed in what is given to the models, or are there discrepancies between the coding language? That was my first question. And second one is, did you have any feedback from GitHub or Microsoft?
I answer the second question first because it's faster. No, I did not try to contact GitHub or Microsoft, and no, I did not get any feedback from them. For the first question, I did not really understand it. Did you mean, were you asking about LLM model training, or were you asking about the language used in my study?
Actually, both of them. I was wondering if there was an impact of the coding language and how those LLMs are made regarding the language.
Yeah, I'm not a specialist about LLM training. LLMs are trained using code from all programming language. You can look at the stack, which is a dataset used for training, for instance, Starcoder. I'll share it in the chat. And basically, the LLM has metadata information about what the language is when it reads the code, but that's all. Naively, I would say that if you use a programming language that's less verbose, that has less characters, mainly less tokens in it, using an LLM to generate code would make the LLM generate less characters, so it would reduce the energy consumption. But I don't think there's other ways it could improve energy consumption. Maybe, it's better. LLMs are better, for instance, in Python and Java than they are in the C language, which makes it so you are more likely to prompt it again to get a correct solution in the C language. Yeah, Olivier says the same thing. The less widespread languages, it is that the LLM will hallucinate. Does that answer your question?
Yes, thanks very much.
Nice. Yeah, Olivier made a good remark about Microsoft talking about Copilot or GitHub Copilot. You should be wary about the terminology that they are using. Eric, do you still have a question, or did you not? Did you forget to lower your hand? So I think that's all right. Is there any other question? Well, that's nice. So I'm going to share with you the link of the slides. So you can find all the slides on this website, and Olivier shared also the link of the paper. So thank you for sharing it. And yeah, that's all for me.
Thanks a lot, Tristan. It was very interesting. Maybe I have a couple of last questions, and the first one is how can Boavizta help you? And the second one is how do you want to maybe leverage on that work within Boavizta?
Well, I don't know how Boavizta could help me, maybe in the far future, by having like a network of people I can talk to for future experiments. But I'm more keen on using what I've learned by using a lot of LLMs and measuring them and the code they generate to help the machine learning workshop. So yeah, that's what I want to do.
Okay, great. Well, thanks a lot.
Just a question, Tristan, not a technical one, but sorry. Thank you first for the presentation. It was really nice. And my question is, because we are recording it, I don't know if you are okay for us to publish it publicly or not, because we publish some of the recording, and if we can reshare later, because I'm sure people will be interested.
I'm perfectly okay with that.
Okay. Thank you again. It was nice, really. Yeah.
Thank you. Thank you all for letting me share this moment with you. It was really nice to present it.